All right, so after a week or so of talking about the forces that moving charges experience as they pass through a magnetic field, we're going to take a step back and we're going to talk about how magnetic fields are produced in general. And since it's moving charges that are associated with magnetism, we're going to first focus on the magnetic fields that are generated by current carrying wires. So the charges are confined to move within the wire. All right, so in that context, we are going to talk about the Biot-Savart law, which we're going to show it in a minute, is the expression that we use to determine the magnetic field at some location in space due to the fact that we've got a current carrying wire in our space as a source of magnetic phenomena. And so the Biot-Savart law is an experimentally derived expression. And so the idea here is that if you've got a current carrying wire, that didn't work. If you've got this current carrying wire, you have got charges moving at all these different locations, right? You've got charges moving all throughout the wire. And if you want to determine the magnetic field at some location, say over here, if you want to determine the magnetic field, you've got to determine the contribution from all of these charges that are moving. And so the way that we're going to approach this is we are going to break up the wire into a small chunk. So we're going to look at like this little spot, and we're going to characterize the magnetic field at location R out here. The magnetic field that's produced is this expression, mu naught over 4 pi I over r squared, and then multiplied by the cross product of dl, that's this little chunk of the wire, dl crossed into the vector r hat. And so just to make sure it's clear what all of these terms mean, first off, mu naught is known as the permeability of free space. It's equal to 4 pi times 10 to the minus 7 Tesla meters per amp. And this is essentially the magnetic equivalent of the permittivity of free space, the epsilon naught that we used back in electrostatics. So that's where the mu naught comes from. It's a constant. I is the current. I here is the current in the wire. dl is this small chunk of the wire, and r is how far away we are. So we're trying to figure out the magnetic field at some location away from the wire, and so r is the distance we are from the wire with that little chunk dl. And so, of course, if you want to know the magnetic field at this location out here, if you want to know the magnetic field here, you've got to integrate over this entire wire. And so the Biot-Savart law is really this right here when you actually integrate over the entire wire. And so the things to keep in mind is what you're integrating over is effectively the length of the wire, this dl here. And and how far away you are from the wire, right? Your point of interest factors into this calculation. Now, this is a vector quantity, so you get the direction from the right-hand rule. The magnitude you get from the definition of the cross product. So the cross product dl cross r, that's just equal to dl times the sine of theta, because the magnitude of the unit r vector is just 1. And so this is the magnitude that you get for Biot-Savart. And of course, you would need to complete that integral to actually get an expression for the magnitude. And then the direction of the B field is taken from the right-hand rule. So point your thumb in the direction of the current, and then wrap your fingers around the wire, and the direction your fingers are pointing as you wrap around gives you the direction of the B field. So it's typically said that the B field curls around the wire, and you can see in these pictures over here, right, that you've got concentric circles. So the B field is getting, in this case, weaker as you move further away. You can tell that because the magnetic field lines are getting further spaced apart, and the field is changing direction as you go around those circles. And a typical way to represent the field is sort of with this face-on view, where you only see the field going into the page and coming out of the page. That's a typical way to represent the magnetic field rather than trying to draw this three-dimensional picture. All right, so we have the Biot-Savart law. Let's go through an example of how to use it. So we want to figure out the B field due to a long straight wire. So I am looking at this point P. I want to try to figure out the B field at that location. And then here's my long straight wire. And so the approach is to break up the wire into small chunks, and then we're going to integrate over the entire wire, over the entire line, and add up all of the contributions, right? So we're going to do an integral here. So the Biot-Savart law, just writing down from the previous page. So the magnitude is going to be just the integral of I dx sine theta over r squared, right? Because the cross product there just gives me that sine theta term. And so I is constant, so I'm going to bring that out of the expression. But let's look at the other terms. Sine of theta, well, if you look at this triangle out here, sine of theta is opposite over hypotenuse. And so sine theta is r over little r. And then little r is, using the Pythagorean theorem, little r is the square root of x squared plus big R squared. So I'm going to substitute this into my expression. And when I do that, I get my new expression for Biot-Savart. Right? It's equivalent, it's just now in slightly different format. And notice I've put in the bounds. If I've got this long or infinitely long straight wire, my bounds are from minus infinity to infinity, right? The extent of the wire goes on forever in the x direction. And I've pulled out the I from the integral because it's a constant. And so one thing that the book mentions, and this is a pretty common thing to do, is that since this problem is symmetric, that integrating from minus infinity to infinity is the same thing as integrating from 0 to infinity and then just multiplying by 2 afterwards. And so so what I've done here is I've multiplied by 2 and then changed the bounds. And so instead of mu naught I over 4 pi, I have 2 pi in the denominator, and then I'm only doing half of the integral. And so the integral is equal to this, and then evaluating at the bounds, you get this expression for the B field, a distance r away from a long, straight, current-carrying wire. So I here is the current in the wire, and big R here is how far away you are from the wire. Now, the direction of the magnetic field produced by this current-carrying wire is determined from the right-hand rule. So in this picture, thumb pointing in the direction of the current, and then you wrap your fingers around. And so up here at the top, the field is coming out of the page, and then at the bottom, the field is going in everywhere along the wire. And then if you're looking at this sort of down the wire, then you also get that same feature in a typical way in the laboratory to check to see the direction of the magnetic field would be to place little magnets, whether they be compass needles, like in this picture, or iron filings, like in this picture. The compass needles, right, all line up in the direction of the oriented along the direction of the magnetic field lines. Just like in electrostatics, when you put a dipole in an electric field, those dipoles would align with the direction of the electric field. So this is how you leverage the Biot-Savart law to determine the magnetic field generated by a current carrying wire. And so this expression right here, right, is a very common and popular expression. And so when you have problems that have long straight wires, you don't have to rederive this. You can just pull this out of your notes. You know that the magnetic field due to a long straight wire is going to be this expression, right? So the field strength drops off as 1 over r, right? As you get further and further away, the field decreases, like 1 over r. So now that we know how to quantify the magnetic field produced by a current carrying wire, we want to investigate what happens when you have two current carrying wires near each other, so two parallel wires. Well, we've got wire 1 over here on the left, and then we've got wire 2 on the right, and we want to determine what's the force on wire 2. Now, there's definitely going to be a force because wire 2 has a current running through it, and wire 1, which has a current running through it, is generating a magnetic field. And so there's definitely going to be a force on wire 2. That force is going to be ILB, right? Because the orientation here is that the current turns out perpendicular to the B field. So what B field is generated by the fact that current is going through wire 1? Well, that's over here in this picture. So let's take a look. This is looking from the top down. So we've sort of rotated this picture by 90 degrees. And when you look down at I1, here is the current carrying wire, and then you get a B field curling around, right, sweeping out circles. So at the location where wire 2 is located, the B field is equal to this expression, mu naught I1 over 2 pi r, right? Just depends on the current in I1 and how far away you are. So that's the B field at this location. So that's what's going to go into this expression right here. The length is just L, the length of the wire, and then I2 is whatever the current in the wire 2 is. So when you substitute all those in, you get this expression for the force on wire 2. So it's just ILB, and it happens to be the case that the B that wire 2 is placed in is generated by a current carrying wire nearby. And so that means if you divide both sides by L, you can talk about the force per unit length. Right, so if you didn't actually know the length, then you could just say the force per unit length is just mu naught I1 I2 over 2 pi r. So the force between these two wires depends on the current in each of the wires, and then also the separation. So what this means in practice is that if I1 and I2 are in the same direction, then the force is an attractive force, and the two wires will move together. And if I1 and I2 are in opposite directions, then that force is repulsive, and they will move apart. All right, so in this video, we went through how to quantify the magnetic field produced by a current carrying wire, and then just looked here at the force between two current carrying wires. And what we'll do for the rest of the week is look at how to determine the magnetic field from a loop of wire, and then go to the more general technique of using what's known as Ampere's law to figure out the magnetic field generated by a current carrying wire. And this is exactly analogous to using Gauss's law to determine the electric field due to some charge distribution.